The Dirac equation is one of the most important equations in modern physics, marking a profound leap in our understanding of the quantum world. It was the first equation to successfully merge quantum mechanics with special relativity, providing a more complete and accurate description of particles like electrons. In today's video, we would take a short tour in the life of the purest soul of physics, Paul Dirac, his major contributions, his monumental work, the Dirac equation. You will not only learn in this video what is Dirac equation, but also understand each and every component, features and their roles that it plays in modern physics. My name is Shaunak and you're watching this video on my channel, Physics for Students. Welcome to this fresh new video on what is Dirac equation. Before understanding this wonderful, beautiful equation of physics, let us take a quick tour into the life of who was Paul Dirac. Paul Adrian Maurice Dirac was an English mathematical and theoretical physicist who is considered to be one of the founders of quantum mechanics. Dirac laid the foundation for both quantum electrodynamics and quantum field theory. He was a Lucasian professor of mathematics at the University of Cambridge, a professor of physics at Florida State University, and a 1933 Nobel Prize in Physics recipient. Now, as you can see, this is the house where Dirac was born. I've taken it from the internet, and if I highlight this blue plaque, and the address reads 14 Monk Road, Bishopston, Bristol, and if I highlight this blue plaque, it would look something like this. Yes, this was commemorated after Dirac's death. A Nobel Prize laureate in 1933 who revealed the secrets of quantum physics and antimatter, born in the house and lived until 1913. That means for about 11 years he lived in this house, and the nearby road was named after him as the Dirac Road. Now here is the, I would say, photograph of a family portrait, and I have been able to decipher. This is Charles Dirac, father of Paul Dirac. This is actually Paul Dirac. This is Felix, his elder brother, his sister Betty, and this is his mother Florence. Florence Hannah Dirac was born to a Cornish Methodist family. She was named after Florence Nightingale by her father, a ship's captain who met Nightingale while he was a soldier during the Crimean War. Now, there is a tragic event which happened to his brother, Felix Dirac. Felix Dirac actually wanted to become a physician, but his father forced him to study mechanical engineering at Bristol. He obtained a third-class degree and he started working as a draftsman with an engineering firm. Reginald committed suicide at 24. After this incident, Dirac was totally alienated with his father. Perhaps Dirac thought that his father was in some way responsible for his brother's suicide. Dirac in a letter later recalled, "My parents were terribly distressed. I didn't know how they cared so much. I never knew that parents were supposed to care for their children, but from then on, I knew." Well, that is a tragic event when Reginald actually committed suicide. Maybe whatever be the reason, he wanted to study something, or maybe for some other reasons. Now, Charles Dirac and the children, I mean to say Dirac's family, were officially Swiss nationals until they become naturalized on 22nd October 1919. Dirac's father was a strict and authoritarian, although he disapproved of corporal punishment. Charles Dirac forced his children to speak to him only in French so that they might learn the language, and he was a French teacher in a school in Bristol. When Dirac found that he could not express what he wanted to say in French, he chose to remain silent. Dirac had a strained relationship with his father, so much that after his father's death, Dirac wrote, "I feel much freer now, and I am my own man." That was kind of a strained relationship which he had with his father. Now this was actually the school, as you can see on the screen, Bishop Road Primary School. This was a school where Dirac was educated, and then he went to the All Boys Merchant Ventures Technical School, where his father was a French teacher. Now Dirac studied electrical engineering on a City of Bristol University's scholarship at the University of Bristol's engineering faculty, which was co-located with the Merchant Ventures Technical School. Shortly before he completed his degree in 1921, he sat for the entrance examination for St. John's College, Cambridge. He passed and was awarded a 70 sterling scholarship, but this fell short of the amount required to live and study for Cambridge. Now, despite having graduated with a first-class honours Bachelor's of Science in Electrical Engineering, the economic climate of the post-war depression was such that he was unable to find work as an engineer. Instead, he took up an offer to study for a Bachelor of Arts degree in mathematics at the University of Bristol, free of charge. In 1923, Dirac graduated once again with first-class honours, and he received a £140 scholarship from the Department of Scientific and Industrial Research, and this was sufficient for him to continue his further studies. In 1937, Dirac married Margit Wigner, a sister of physicist Eugen Wigner, and a divorcee. Dirac raised Margit's two children, and these are the two children, Judith and Gabriel, as if they were his own. Paul and Margit Dirac also had two daughters, Mary Elizabeth and Florence Monica. Margit, known as Mancy, had visited his brother in 1934 in Princeton, New Jersey, from the native Hungary, and while at dinner at the Annex restaurant, he met the lonely-looking man at the next table. This account from a Korean physicist Y.S. Kim, who met and was influenced by Dirac, also says, "It is quite fortunate for the physicist community that Mancy took good care of our respected Paul Adrian Maurice Dirac. Dirac published 11 papers during the period of 1939 to 1946, and Dirac was able to maintain his normal research productivity only because Mancy was in charge of everything else." Well, that is why it is said that behind every successful man there is a woman, and we can see Margit Wigner actually contributing a lot and helping Dirac to free of the other mundane work so that he can concentrate on his own study. Well, this is actually a whirlwind tour into the life of Paul Dirac. But what were the major contributions of Paul Dirac? Let us look into this first. Now, as we know that he formulated the Dirac equation, which actually showed a lot of things. We are going to cover this, but actually describes the fermions and predicted the existence of antimatter. Remember, when Paul Dirac actually framed this equation, he thought that his equations were wrong. And he is considered to be one of the founders of quantum mechanics, and he actually developed key principles of mathematical formulations. The equation predicted the positron, which was the antiparticle of electron, and it was experimentally discovered later by Carl Anderson. He contributed to the development of quantum electrodynamics, a theory describing how light and matter interact. Well, if you think that this is all, absolutely not. This genius person has got many other contributions. First is that he introduced what is called the bra and the ket notation, and we use it almost in daily in our college classes and universities, and he hypothesized the existence of magnetic monopoles, which means that a magnet might have a single magnetic pole. This is it's a very difficult book, The Principles of Quantum Mechanics. It is an influential monograph on quantum mechanics written by Paul Dirac and was first published by Oxford University Press in 1930. Dirac gives an account of quantum mechanics by demonstrating how to construct a completely new theoretical framework from scratch. Not a very easy book to read. And other than that, he also contributed in developing what is called Dirac delta function, Dirac algebra, Dirac operator, second quantization, quantum theory of radiation, and a lot. And all these contributions ultimately culminated in winning the greatest prize in physics, the Nobel Prize in Physics in 1933, which he shared with Erwin Schrödinger, and for the discovery of new productive forms of atomic theory. Now this pionest soul of physics also had a very strange character, and that is quite worth noting in today's video, Dirac's personality. I will just take a few minutes to explain that, and you will be surprised and feel very strange after listening to these stories. Now Dirac was known among his colleagues for his precise and taciturn nature. His colleagues in Cambridge jokingly defined a unit called a Dirac unit, which was 1 word per hour. Now, when Niels Bohr complained that he did not know how to finish a sentence in a scientific article he was writing, Dirac replied, "I was taught at school never to start a sentence without knowing the end of it." An anecdote from a 2009 biography reviews recounts a story from August 1929 when Heisenberg and Paul Dirac were sailing to a conference in Japan. Both were in their 20s, unmarried. They made a peculiar pair. Heisenberg obviously was a charming ladies' man who loved to flirt and dance, while Dirac, described by biographer Graham Farmello as an Edwardian geek. During one such occasion, Dirac asked Heisenberg, "Why do you dance?" Heisenberg replied, "When there are nice girls, it is a pleasure." After considering this, Dirac earnestly asked, "But, Heisenberg, how do you know beforehand that the girls are nice?" Margaret Dirac told both George Gamow and Anton Capri in the 1960s that her husband had said once to his house visitor, "Allow me to present Wigner's sister, who is now my wife." Now this is very strange, and if you really want to read a more strange and wonderful biography of this famous person, Paul Dirac, I would just say what I uttered just now, the biographer Graham Farmello. This is a wonderful book, The Strangest Man, The Hidden Life of Paul Dirac, available at Amazon. You can go ahead and check it. It will be a very good book and a very great biography to read through it. Now, the influence of the importance of Dirac's work have increased with decades. In 1984, Dirac died at Tallahassee, Florida, and was buried in Tallahassee's Roselawn Cemetery. Dirac's childhood home in Bishopston, Bristol, is commemorated with a blue plaque, which I have shown you earlier, and the nearby Dirac Road is named in recognition of his links with the city of Bristol. Well, that completes his personal life, his different kind of a character, and also his contributions. And we come to the central part of our video, that is, what is Dirac equation? Well, I understand the Dirac equation is a little bit complicated because it takes into account 3 pillars of physics. One is classical physics, special relativity, and the quantum mechanics. But I would take simple equations and will try to fairly tell you as simple as I can what is this Dirac equation all about. Now, first of all, let us look into the original version of Dirac equation. Don't worry about those signs, because I'm going to take a modified version of this and I'm going to explain to you. Now, this was the original form, which can be written like this, or using what is called Feynman's notation, cancel notation. It can also be written as this. Now, each of these are Dirac equation used in different notations. Now, what is important about this Dirac equation are certain features. Now, these features are now then mathematically written, and we will discover that mathematically. So first understand that this is a relativistic wave equation. That means unlike Schrodinger equation, which is a non-relativistic wave equation, Dirac's equation is a relativistic wave equation. It describes spin half particles, the fermions, which are specifically electrons. Now you might have a question, was that during that time Schrodinger did not describe the spin of the particles? Well, during that time, to be honest, as far my knowledge of history goes, the concept of spin was not quite predominant. The concept of spin was not quite clear. And also the discovery of what is called spinors were not done during that time. So Schrodinger equation actually does not take into account the spin. The first thing, which is most important, it brings together special relativity and quantum mechanics. So in our search for a theory of everything, this is a unison which marries together relativity and quantum mechanics. Yes, this is very important, that it predicted antimatter, because when Dirac actually discovered, he thought his equations to be wrong. It also gives a complete description of spin-half particles, that means fermions, which were not taken into account in Schrodinger's equation. And the foundations of quantum electrodynamics, which is actually resulted into quantum field theory, actually contributed and resulted from Dirac equation, and it also explains the fine structure of hydrogen. Well, these are the major contributions, I would say major implications, but there are many other implications which we will discover slowly. And first we will look into this Dirac equation, and I'm going to explain you component by component what those equations, what those symbols mean, what do they contribute. Remember, might be there are some things which are not very clear to you because it contains a lot of advanced mathematics. However, I will try to make it as simple as possible. So the first unit that comes is the I, the imaginary number. Now, it is quite obvious that quantum mechanics, the Hilbert space, everything deals with imaginary number. So it would allow the wave function to include oscillatory behavior, and it accounts into what is called the probabilistic behavior. Now, not only we can take the probabilistic nature of quantum particles, but remember that it has to work in hand in glove fit with special relativity. So observables like position and momentum, which are represented by Hermitian operators, the Dirac equation actually makes consistent with the underlying quantum framework. That means it actually incorporates I so that it can maintain consistency. What is also important is that in quantum mechanics, wave functions we know are generally complex valued functions. So the presence of the imaginary unit is fundamental in the Schrödinger equation, which actually guides the evolution of a quantum system. Now from here, what we see also is that the Dirac equation actually unifies space and time. And don't worry about this, I will just explain to you what is that. Now it unifies space and time into a four-dimensional space-time continuum. So the imaginary role unit actually plays a very important role in that. Now you see that the time component, which I would say the time component in the context of special relativity, the time component, which is this one, and the spatial component, this one, must be treated differently. Why? Because time and space have different signs in what is called the space-time metric. So the imaginary unit I helps actually to balance these components. Now if I take this one, right, so what it tells you is that it corresponds to the energy operator in the quantum mechanics, and what it ensures that energy is treated consistently with momentum in a relativistic framework. This is the relativistic framework. This is quite known. E is the energy, P is the momentum, M is the rest mass, and C is the speed of light. So what happens in here, that the inclusion of I, which we are talking about, ensures that the Dirac equation respects the relativistic relationship between energy and momentum. And as you can see that I del 0 corresponds the energy operator in quantum mechanics, and it ensures that the energy is treated consistently in a and with momentum in what is called a relativistic framework. So from here, what we can get is that this imaginary number was present earlier in the Schrödinger equation, isn't it? Here it is already there. And the Dirac equation is considered to be relativistic equation. So Schrödinger equation being non-relativistic and Dirac equation being relativistic, both of them has got I. Now this has got a tremendous influence. The understanding is that under, I would say, slow movement of particles which are traveling less than the speed of light, what is happening is going to do that the Dirac equation is going back to Schrödinger equation. So it can actually go back to Schrödinger equation. And you understand that this is also something which is similar to general relativity, because the Newton's laws of motion, I would say a general theory of relativity, all these equations under a slow moving dust particle which has got a less gravitating force will go back to the Newton's law. Similarly, if you don't consider the speed of light, particles which are less will reduce back to Schrödinger equation. And if it reduces back to Schrödinger equation, this I and this I has to be matched, or there should be a kind of a I would say compatibility in terms of understanding. So from here, what we can say that Dirac equation reduces to the Schrödinger equation in non-relativistic limit, and because Schrödinger equation includes I in the time evolution term, the Dirac equation also includes I to maintain the consistency when transitioning between relativistic and non-relativistic regimes. So what can we deduce from this? This one. First one is that we include the I because to complex nature of quantum wave functions. It ensures the equation is Lorentz invariant because as we are taking in special relativity, it has to obey the Lorentz transformation, isn't it? And it guarantees that operators are in the equation are Hermitian and preserving the physical interpretation, and it maintains consistency because it has to go back under slow conditions to the non-relativistic Schrodinger equation. So this is the first term which we have discovered, which is the I. The h bar or the Planck's constant is something which I am not covering. We know it is just a Planck's constant. The next very important, a little bit complex concept which comes is this. And these are actually called gamma matrices. A sigma, the gamma with a mu on the top. Now let me tell you what are gamma matrices. Now gamma matrices are basically simple matrices which has got a 4x4 matrices, and they were actually introduced as gamma matrices or Dirac matrices because there was a need, and what is that need? We will just look into that, of the wave of the electron. So the gamma matrices are a set of conventional matrices with specific anti-commutation relations. Now this is important. The specific anti-commutation relations which will actually represent that and follow the Clifford algebra. I will come to this part later, but let us understand what is gamma matrices and how it plays an important role in the Dirac equation. Now you see there, I will show you the gamma 0, gamma 1, gamma 2 and gamma 3. These are 4x4 general matrices. Now what becomes very important is this one. Now all of this, as you can see, this one, this one, this one and this one, all of this has got the indices 0, 1 or 2 or whatever you can put it as mu, which we have done right on the top. Right on the top. So what does that mean? It means that it is basically a combination of 4 contravariant gamma matrices. I hope you are all aware about covariant and contravariant transformation, because the indices on the top, as I mentioned in one of my shots, that just here you do a transpose. So any indices climbing up is a contra, any indices going down is a covariant. So these, as you can see, ultimately 0, 1, 2 and 3 are basically 4 indices. And these indices are contravariant indices. Now you see these indices are actually representing the 4-dimensional space-time. 0, 1, 2 and 3. Now you might have a question which I am going to answer, that why do we need a contravariant and not a covariant? And for this, there is a concept which is called relativistic invariance. There are certain things which actually do not move, and we are going to look into that into next. Now those who are aware about special theory of relativity, you know that this 4 position, 4 momentum and 4 vector actually transform appropriately under Lorentz transformation. This is the basic idea of special relativity. And how do they transform? They transform contravariantly, I'm sorry. So if I take this equation, now you see there is a del mu and the indices in the lower, that means it is a covariant. So what we can deduce from here is that the Dirac equation involves the 4 gradient. We were going to look into what is a 4 gradient, which is covariant. And why it is required? Because a contravariant and a covariant together will construct a scalar. And why do we need a scalar? Because if we get a vector, it would be a problem. We need a scalar. Why? Because it will be invariant under Lorentz transformation, and you need to contract this with a contravariant tensor. So let me repeat again that this del mu is a covariant gradient tensor. It has to be coupled up with a contravariant vector or contravariant indices, and then it will only produce a scalar, and scalar will be invariant under Lorentz transformation. So this has a contravariant index, this has a covariant index, and beautifully the master stroke that Dirac made was that the contraction gave a scalar quantity, and this actually shows that it is a Lorentz invariant. So overall I can say that the equation, the Dirac equation, is Lorentz covariant in nature. So the contravariant vectors transform in a way obviously which will preserve the Lorentz transformation. And by using contravariant gamma matrices, we ensure that the Dirac equation can go under those transformation and the Lorentz transformation is being maintained. So from here we can say this gamma mu, these indices, actually these are spatial indices, 0 for time, 1, 2, 3 for space. So since space-time coordinates are typically transformed as contravariant vectors, the gamma matrices also inherit the contravariant property. And from here we can also say that gamma matrices must transform in a specific way under Lorentz transformation. Why? Because it has to be a Lorentz invariant. And the transformation property aligns with the behavior of contravariant vectors. But what you are thinking to be truly covariant and contravariant, it is not so. It has got a very subtle thing which I am going to tell you. So from here, let me show you a bigger picture. So the 4 position, 4 momentum, 4 vector, they are contravariant in nature. We get the gamma matrices which is contravariant in nature. Now suppose in a Cartesian coordinate we get x0, x1, x2 and x3 in a Cartesian vector, and we do a basis vectors, then that it will transform contravariantly, and it shows like this. Now if I take the Cartesian coordinates del 0 by del x0, that means how the x coordinate transforms, the y coordinate transforms, the 1, 2, 3 and so 0, 1, 2 and 3. So that is how it is. This is how the Cartesian coordinates and the basis vector transfers. But if I change the vectors to prime vectors, x prime 0, x prime 1, whatever the way it is changing, then the tensor component would be the contravariant. See, x prime mu, the del x prime mu, del x nu, x nu. That means it is gone in the upstairs. That means again it is what is called the contravariant transformation. So space-time coordinates, 4 velocity, etc. from special relativity, they transform contravariantly. This means they transform in the opposite way. So the gamma mu, which we have taken the gamma matrices, they transform in the same way, and they naturally inherit the contravariant property. So these indices are now written in a much more compact manner. Obviously, as we don't write 0, 1, 2, 3, we will write it as gamma mu. And what is important is that in the Dirac equation, the gamma matrices, when they're used, they take place of a spinor field. The spinor I will come later in this video only. So the role is to maintain the equations covariant when the spinor field undergoes a Lorentz transformation, and they ensure that the derivatives and other terms of the Dirac equation transform correctly. So from here, what we can tell is that this is very much which is covariant in nature. This is covariant in nature. This is contravariant in nature. These are the 4 vectors in special relativity that transform in contravariant nature. So things match. And the gamma matrices, when these acts on the Minkowski space, they become space of spinors. And they follow what is called the Clifford algebra. And remember, it is the indices of the gamma matrices that change either contravariantly in this case, but not the matrices themselves. So it would be wrong in a strict manner if you think that gamma matrices actually behave like tensors. Actually they are not. They actually will take the form of a spinor which will actually follow the Clifford algebra, but on a very hand wavy manner we can tell that yes, it takes a contravariant nature due to the change of contravariant for the 4 vectors. So from here what we can tell is that the gamma matrices, remember, they are not exactly tensors. So it would be very wrong mathematically if I say they are tensors. So you can just think of gamma matrices like matrix valued vector in Minkowski spacetime. So the carry vector like indices, just like vector like indices, but behave differently under transformation because they will follow what is called a spinor transformation. Here it is. While contravariant transformation fundamental to special relativity, their direct connection to gamma matrices is through the role of diracspinors, and diracspinors, as we will see, is a totally different ball game. It transforms in a different way. So what we can say at the end is that when we take this equation, this gamma mu is basically contravariant. The del mu is a covariant. So if we contract the indices of a covariant and contravariant, what will happen? We will get a scalar quantity. And why do we need a scalar? Because if we get a scalar, it will make no changes and the equation will be Lorentz invariant, and that is the target of Dirac equation, to make it Lorentz invariant so that it remains the same under any kind of a Lorentz transformation. I can talk a lot about gamma matrices, but I have got other things which I can tell you. So let us move into the next part of our Dirac equation. We will take this partial derivative mu, which is called the foregradient. The foregradient, as you understand, is just the gradient as we do in general physics, the classical physics. So this mu has got 4, x0, x1, x2, x3. Out of that, this one is the time, and this one are the spatial coordinates. So temporal and spatial. So I'm trying to give you a fairly intuitive idea. So what happens is that this del mu You can say that they describe how the wave function changes with respect to both time and space. Obviously, if both the things are changing, then only we need a partial derivative. Otherwise, a normal derivative will do. So this is essentially in relativistic context, because why? Time and space are intervened into a four-dimensional space-time. So gamma nu is paired with a four gradient del mu, which this one is a contravariant vector, this is a covariant vector, and to correctly contract it, we get a scalar which transform under Lorentz transformation. Now, when we talk about space and time, one thing which is very noteworthy is that in Newtonian concept, we have got a separate space, we have a separate time. X-axis is space, y-axis is time, or z-axis or whatever. Now, with the advent of special theory of relativity, we know that this happened, the space-time continuum. So, space and time are not two different coordinates. So, instead of gradient, we have a four gradient, right? Because we have got the 3 dimension of space and 1 dimension of time. So, as it tells that something changes in both space and time, and hence we need partial derivatives, and hence we need a partial mu, and this mu are basically x, y, z and t. That means the 3 dimensions of space and t begin the dimension of time. So what happens is that this is the general partial derivatives, right? Del by del x, del by del y, and we do it in the general calculus. So it actually describes how the particles' properties change in space-time. Remember that the Dirac equation is basically predicting the behavior of fermions, that is electrons, and they have got a half spin. So in order to know the time evolution of a particular particle, which Schrodinger had done earlier in a non-relativistic manner, here the both and space and time is intervened. So we need a component where the space-time is evolving, and that is what is that 4 gradient component. So the 4 gradient actually ensures that the Dirac equation is again Lorentz invariant. And this invariance is crucial as it ensures consistency with the principles of special relativity. So we are done with the first component, that is the I, the second component which is the gamma matrix, and the third component which is the gradient, the 4 gradient. Now we come to the most important, a little bit confusing and a weird kind of a concept, which is this one. And remember, this is not the usual wave function. What is this? This is actually a wave function of a fermion, but as I have written, unlike the wave function Schrodinger equation, it is which was a scalar function. This is a spinor. Now, spinor is itself a very advanced topic in physics, and this is not the right video to explain a lot about spinor. You might have a question of why Dirac has taken a spinor, not a wave function. But what I can tell you is that a spinor is basically a mathematical object that describes a quantum state of particles which spin have. Remember, earlier to that we have already defined particles which has an integer spin, 0, 1 and so on. But the basic idea of Dirac equation is to include the spin have particle. And spin-up particles are actually quite different. I will explain it later in some video. So spinors, remember, spinors are not Lorentz invariant, neither they are covariant. It is totally different. So spinors have component that transform in a specific way under Lorentz transformation. And this psi is a 4-component spinor, and each of them are a complex valued, and I will show you how it looks like. It looks like this. So the first 2 spinors, psi 1 and psi 2, they represent spin up and spin down, that is of the electron, and it has got a positive energy. The psi 3 and psi 4, these also represent spin up and spin down, but with a negative energy. As I told you that anti-particles or anti-matter was predicted, this was that. The spin up and spin down, again spin is a very intrinsic property of electron. It is not the linear kind of a momentum. It is basically what you call an angular momentum. I will take it up later in a video. A spin of electron is not what you think, that it just rotates like a spinning top or a planet which is going around. It is an intrinsic property. It is what is called the angular momentum. It is not a linear momentum which has got. So this is the 4-component spinor. So if the first 2 are showing the positive and the second 2 are showing the negative energy, and they represent the spin up and spin down because we need to register the spin up particles. Now the physical interpretation, if I squared the modulus, obviously it will give the density of finding the particle at where it is. So from here what we can deduce is that if I take from this Dirac equation the spinor, so spinors have components which transform in a specific way. I'm not explaining that. Don't confuse it with the usual Lorentz transformation. It has got a different kind of a understanding. The Dirac spinor again is a bispinor. Polymatric can also be a spinor, but this is a bispinor. And it takes into account the particles and antiparticles, so it is a bispinor. The Dirac spinor incorporates spin directly, and it describes elegantly the spin half particles. The Dirac equation naturally predicts the existence of antiparticles, and obviously the Dirac spinor incorporates the effects of special relativity. So if you now look in the equation, you have done with I, h bar is the Planck's constant, gamma mu, gamma matrices, del mu is the 4 gradient. You have done with the psi, which is the spinor, not a usual wave function, and we are left with last two things which are fairly easy, the m and the c. So the m actually is the rest mass of the particle. This is the intrinsic mass of the particle, and c obviously is the speed of light. So the multiplication of c, m multiplied by c, ensures that all the terms in the Dirac equation have consistent units and are relativistically invariant. Now the mass term is important because it gives the inertial property which contributes to the relationship between energy and momentum, and the speed of light in the Dirac equation guarantees that the equation respects relativistic nature of space-time. That means those particles which are moving close to the speed of light. You might have a question why this equation is equated to 0, but as you know, I completed this video and the entire script at 4 o'clock. At 4 o'clock in the early morning. I was feeling really a bit sleepy, so I will take up these questions in the next part. So we have some unanswered questions. Why we need a relativistic equation? Why Schrodinger equation cannot explain the relativistic part? What is the importance of Dirac equation? What were the limitations of the earlier effort, that is the Klein-Gordon equation? What is anti-commutation of gamma matrices and Clifford algebra? And why Dirac used spinors instead of wave functions? All this I'm going to take up in the next part of the video, because I was really tired in making up this script. So that's all for the first part. I would say an initial understanding of what is Dirac equation, why it is relativistic, and so on. So thank you very much for watching this video. If you have liked this video, do not forget to hit on the subscribe button on my channel Physics for Students, and click on the bell icon to get all the notification from Physics for Students. You can write to my this email ID. You can also subscribe to my other channel where I put up videos on general theory of relativity. You can follow me further on my Facebook, LinkedIn, Instagram, and Twitter account. Physics for Students will be soon back with many more videos, but this was the primary and initial introduction of what is a Dirac equation, and I hope you liked it. Please do put in your comments, and I will see you soon in the next video. Till then, may the good Lord be with you.